This is a presentation of our results on token sliding reconfiguration of dominating sets in circle and circular R graphs. This is a joint work with Alice Joffard. So token sliding reconfiguration is a reconfiguration problem. So what is a reconfiguration problem? It can be seen as a puzzle. A puzzle is basically a one-player game where some player wants to make a series of moves and is trying to accomplish some goal. So probably the most famous reconfiguration problem is the Rubik's Cube. So the question is, given my current position, can I reach a fixed target position? Which is this position where all the colors, all the faces are the same. So there are many applications of reconfiguration problems to many fields. So of course to puzzles and games, but also for random sampling, bioinformatics, discrete geometry, and so on and so on and so on. So in reconfiguration, usually we are asking ourselves three main questions, which are the following. So the first one is the reachability problem. So given two configurations, is it possible to transform the first one into the second one? So given my current position of the Rubik's Cube, is it possible to reach the nice target configuration where all the colors on all the faces are the same? Then there is a more general question, which is the connectivity problem. So given any pair of configurations, is it possible to transform the first into the second? So for instance, for the Rubik's Cube, we know that the answer is no. We know that basically the configuration graphs are several connected components, so which means that there are some configurations from which you can't reach this really nice target configuration. And then when you know that a transformation exists, there is a question which is, okay, what is the length of the shortest sequence between my position and the target one? So if you are trying to solve the Rubik's Cube as fast as possible, you want to find a short sequence. And of course, all these questions have their algorithmic counterpart, which is, can we solve these questions fast? And so for instance, in polynomial time, in FPT time, or is it hard? Is it NP hard or P-space hard? And so today we will focus on the reachability problem for dominating set reconfiguration. So probably most of you know what is a dominating set, but so a dominating set is just a subset of vertices of a graph such that the closed neighborhood of this set is equal to V. So which means that if you select this set X of vertices plus its neighborhood, then you should contain the whole set of vertices. And basically, for reconfiguration, it's usually more simple to consider these sets of vertices as a set of tokens. So we will imagine that a dominating set is just a set of tokens placed on vertices whose closed neighborhood is the whole set of vertices. And we will say that two dominating sets are adjacent if the second one can be obtained from the first one by sliding a token along an edge. Okay, so here, for instance, you can slide this bottom red token on this above token by sliding along this edge, and you are still a dominating set. And we will say that there exists a transformation from S to T if there exists a sequence of adjacent dominating sets transforming S into T. And the problem now is, okay, given a graph G and two independent sets, is it possible to transform S into T? Okay, and so before stating formally our results, let us give so some of the results obtained by in a recent paper of Bonamy, Dorbeck, and Ouvrard. And so the first one they obtained, they show that this dominating set reconfiguration problem is P-space complete, even restricted to some small classes of graphs such as bipartite graphs, split graphs, or planar graphs. And they ask the question, does there exist a hereditary graph class for which minimum dominating set is in P complete, but dominating set reconfiguration is in P? And so what we will, and so they propose a candidate for this question, which is the class of circle graphs. So circle graphs is the graph of intersection of chords of a cycle. So basically here you have this cycle, so and chords on it, and the chords correspond to vertices, and you put an edge between two vertices, for instance between yellow and green, if the corresponding chords intersect. So there is a chord between green and yellow, but no chord between blue and black. No edge between blue and black. Okay, and we show that this candidate is actually not the good one, because the problem is p-space complete on circle graphs. And they also give some positive results on their paper. They show that there exists a transformation between any pair of dominating sets for interval graphs. Actually, their results is slightly more general, but one of the most important graph class contained in the class of graph for which they show that is the class of interval graphs. And they ask, okay, is dominating set reconfiguration also polynomial on circular R graphs, which is a generalization of interval graphs? So interval graphs correspond to intersection graphs of intervals of a line, and circular R graphs are basically the same, except that instead of taking intervals of the line, you are taking intervals of a cycle. Okay. And what they remarked is that their results cannot be extended to circular R graphs, because, for instance, if you take a cycle of length 0 mod 3 like there, you have three dominating sets here of size 3, for which are completely frozen, which means that you can't move any vertex there. Okay, so it is not always possible to transform any dominating set into any other, but maybe the problem is still polynomial, and we show that the answer is positive. Dominating set reconfiguration is polynomial on circular R graphs. So now let me sketch a bit the proof of both results in a couple of minutes. So first, dominating set reconfiguration is polynomial on circular R graphs. So what is the idea of the proof? The idea of the proof is to use as a black box the results of Bonamy, Dorbeck and Ouvrard, which guarantees that on interval graphs the answer is always yes. Basically, if the intersection is non-empty, then we claim that the answer is always yes, because we simply have to cut the cycle on a common vertex, and by cutting the cycle on this common vertex, basically now we can open the cycle and just get an interval graph rather than a circle graph. And we know that we can transform any dominating set into any other, which means that basically we can just align the other vertices of the rest of the dominating set without changing this specified vertex of the intersection. And so the answer is positive. The answer is always positive. And so now the question is, what happens when the intersection is empty? And so when the intersection is empty, basically what we will try to do is to shift some vertices of the dominating set in order to get a non-empty intersection if possible. So let me describe a bit the transformation in a few pictures. So imagine that we have this dominating set there, and now what we will do is that we will again cut the graph in order to obtain an auxiliary graph, which is an interval graph. So how can we do that? So let's take this bottom red vertex, and so we can assume that this vertex is maximal by inclusion, because if it's not, we can replace it by a larger vertex with a larger interval which dominates more people. Okay, And now we just cut, we will remove this vertex, but before removing this vertex we will add two new vertices, one at the, basically at the left there, one at the right. Okay, and so these two vertices will be in any dominating set at the end, and they will simulate the fact that we want this vertex to be in the dominating set. And now, okay, so now let's remove this bottom red vertex, and now for any possible vertex we remove, which was intersecting this long interval at the bottom, we remove this vertex and create instead a vertex, a new vertex here at the left, and so on and so on. And so we remove all the vertices like that, and what we obtain instead is an interval graph. Okay, and so now we have an interval graph, and so we know, using the result of Bonamy, Dorbeck and Ouvrard, that we can transform any dominating set into any other. Okay, so, and what we can do, for instance, is move the dominating set as far as we can to the right. Okay, oh yeah, before doing that, we just add two new vertices, so there's two, that only sees the two new vertices, two new red vertices there, just to be sure that any dominating set contains these two vertices. Okay, and so now what we can try to do is to push the red dominating set to the right, for instance here by moving this one there and this one there, and by doing so we claim that this transformation we just did on this interval graph can actually be performed also in the original circular R graph, moving this vertex there and this vertex there. And what you can remark now is that by pushing everything to the right, we have found a vertex in the intersection. So now this vertex and this vertex are in both independent sets, so now in both dominating sets, and so now the intersection is non-empty, and since the intersection is non-empty, the answer is positive. And if the intersection is still empty, then we can try to repeat again and again this transformation. Okay, so there are a lot of ideas that are hidden there, but basically that's the idea of the proof. The piece-space completeness on cycle graphs. So the idea of the proof is to combine two existing results. The first one is the result of Gopalan and some co-authors, which ensures that SAT reconfiguration is piece-space complete. And the second is a result of Kiel from 93, that is a reduction from SAT that ensures that minimum dominating set on circle graphs is NP-hard. And so when we combine these results, there is a huge technicality when we try to adapt the Kiel reduction for reconfiguration, which is the fact that minimum dominating sets are rigid somehow, in the sense that we can't really modify this dominating set of size k there, and we can't reach anything from this dominating set, and we can't make some SAT reconfiguration with them. So to overcome this problem, we need to consider dominating set of size k plus 1 instead. But when we consider this dominating set of size k plus 1, we lose some control on how much they correspond to assignment of variable that satisfy the SAT formula. And so we need to create additional gadgets to control the structure of this dominating set, to guarantee that they are somehow still close from an assignment of the SAT formula. And that when we make a move on this between dominating set on this graph, then it corresponds somehow to a move in the SAT reconfiguration framework. So to conclude, I want to mention two open problems. So the first one is the problem that was raised by Bonamy, Dorbeck and Ouvrard, which is, does there exist a hereditary graph class for which minimum dominating set is in P complete and dominating set reconfiguration is in P? So at first glance, such a result might seem a bit counterintuitive, in the sense that usually reconfiguration problems are harder, but there are some cases where they becomes simpler, because when we are looking at a reconfiguration problem, we already have a solution, And the fact that we have a solution might simplify a lot our life. And so, for instance, for 3-colorability reconfiguration, we know that the problem is in P, while it is so 3 coloring of a graph is NP complete. And another line of research might be the existence of FPT algorithms, since in most of the graph classes the problem is P-space complete. Is it possible to derive some FPT algorithms parameterized, for instance, by the size of the dominating set? So thanks for your attention.